Okay, finally. Yeah. Light. All right. So we were here last time. First, let me recall where we are. Our goal, we want to prove the algorithm we did, we derived is optimal. Optimal, all right? Yeah. To do that, yeah, algorithm to solve the minimum problem, minimum of the array. Yeah. Yeah. So the detail we did last time. Yeah. Remember, the previous slide. So we use n-1 comparisons to find a solution. N-1. Yeah.
That sounds like the worst case efficiency.
Yes, worst case efficiency. Yeah.
Nobody has no time to do first, we just want a faster computer already.
Nobody what?
Talking about you try the brute force algorithm we were running.
Yeah, brute force. Yeah, all right, you mentioned that. Yeah, pretty much brute force. Yeah. Good. Yeah, good point. Yeah. So I agree, because we do not use any special technique. Yeah, I agree. It's a brute force algorithm. Yeah. All right. Now the question. Our goal, we want to show this is the best solution. The best solution here. So here, first let's understand. What's the meaning of the best solution? Yeah. Other? It looks like there is no confusion here, right? Everybody knows the meaning of the best solution. But the question, if I ask you, yeah, when you say the best solution, do you mean nobody can do better than this, right? Nobody can do better than this. But the question, what's the meaning of nobody here? Yeah, let me go to more detail on this nobody here. Do you mean the nobody in this country or nobody in the world cannot improve it, right? Yeah. Yeah. Which would mean nobody in the world, right? Or nobody in the universe. Probably. Yeah. We don't know. Yeah. Or also you need to think about, when we say this nobody, do we only mean nobody currently on Earth? Do we mean that? Nobody currently on Earth cannot find a better solution. My question is it possible after 300 years, 500 years, there is someone that, some scientist, super genius, can find a better solution? Is it possible? Yeah. So when we say nobody, do we include that situation, future, nobody? That question, right? It looks not that easy to answer. Yeah. The answer is we include, even in the future. 1,000 years, 2,000 years, forever, nobody. Okay? We mean that. Then we can say this is the best solution. Nobody in the future. Okay? Yeah. Even if the AI is so powerful, still nobody. Okay? Including AI. How about that? Not just human. Okay? Including AI. All right? Yeah. That's the absolute best solution. Okay? Yeah. All right. So let's try to do that. Yeah. To do that, we need to study all the possible algorithms that can solve the problem. And those possible algorithms, most of them unknown. Okay? So now we need to study unknown algorithms. Yeah. We have to cover all those unknown algorithms. But how can we do that? Yeah. At the end of last class, I give you the idea. We need to discover some common properties for all the algorithms. Yeah. Although unknown, yeah, the details unknown, but we can find a list of common properties of all those algorithms. So we use those common properties to prove it is the optimal. Okay? All right, so let's do it. Yeah. All right. Yeah. All right, let's go to, now we need to, convince people our algorithm is optimal. All right, yeah. To do it, all right, we need to do some preparation. Yeah. So here I talk about, yeah. So in problem solving, yeah. So this question is a very good example, giving us some typical thinking process of problem solving. Yeah. Use our brain, use our brain power to do the critical thinking here. All right. I talk about the real world experience. Yeah. So we need to connect to our real world experience. Yeah. Why we do that? Because here, the main reason we do that for understanding of the problem. We want to understand the problem well. Yeah. So that's another important factor in problem solving. Before you can solve it, with a good solution, you need to really understand the problem well, right? So for understanding, what do you mean understanding? Yeah. Understanding, you need to take a good view of the problem. You really need to comprehend all the useful information related to the problem. Then use the information in a creative way. That's the understanding. Okay? Yeah, that's very important. So here, but how do we understand? Here, we borrow some real world experience to help us understand. Okay? So what kind of real world experience? Yeah. Playing sports game. Yeah. So you're familiar with things like that. Yeah. Typical sports game play. Two players. Okay. One player tries to beat another player. Yeah. We use this kind of relationship to understand comparison. We compare two elements. One element is greater than the other, right? So now we connect to, one player beats another player, right? The reason we connect, we want to understand the whole story better. Yeah. All right? Yeah. All right, comparison. In our comparison, yeah. So one comparison corresponds to one match between two players. Yeah. All right. Then the results. Regarding the results, yeah. Less than, yeah. So here, less than or greater than, yeah. Case. Less than. For our current question, our goal, finding a minimum, right? Our goal is finding a minimum. Then, minimum means we want to find the smallest element. When we do comparison, then the smaller the better, right? Yeah, because our goal is minimum. When we do comparison, we want to pick the smaller one. We do not want to pick the larger one. Okay? That's why here we change the definition. If we get a less than inequality, then we mean the smaller one is the winner, okay? The smaller one is the winner, yeah. Because that's the right direction toward the final result, minimum. Final result is the minimum, okay? The minimum is the final winner, okay? Yeah, that kind of relationship. Equal, tie, greater than, yeah, lose, yeah, all right? That kind of relationship we want to connect, yeah, to help us understand, yeah, all right? Then, but when we do that, when we use our familiar experience to help us understand, but we also need to know these two things are slightly different. Comparison, yeah, so one, phenomenon we want to study, another, sports games we want to study. There is some difference between them. Yeah, not exactly the same. Here, I want to point out the main difference here. What's the main difference? In our comparison, we have a property we call the transitivity property, right? Yeah. Transitivity property in our comparison. What's the transitivity property? Let's recall, okay? In our algebra, regarding the inequalities, we have this transitivity basic property. What's that? If PA greater than PB, okay, and PB greater than PC, then we can say PA greater than PC by transitivity. That's the transitivity property in algebra. Okay? We know PA greater than PB, okay, after one comparison. We also know PB greater than PC after another comparison. Okay? So here PA, we mean player A. Okay? PB player B, thing like that. Then, if we know the results of these two inequalities, then we do not need to compare PA and PC, right? Because we can automatically say PA greater than PC. No need to waste your another comparison, right? Yeah, no need. You can save one comparison. That's the transitivity. Yeah. All right. But in our real world, in the sports game, we don't have this property, right? Yeah, player beats player B, player B beats. Then you cannot say automatically say player A can, player A beats player C all the time. You cannot say that, right? You can say sometimes, right? Yeah, sometimes, but you cannot say all the time. Yeah. But in math here, we can say all the time, right? PA greater than PC all the time. That's the main difference. Okay? Yeah. So we also need to know the difference. So when we apply some, analogy, yeah, because sometimes we need to use analogy to help us do the thinking. So we should be careful in places like this. Okay? Yeah. All right. Next. Then we go one level deeper. Yeah. One level deeper in our understanding. So what's that? Here, based on this transitivity property, then we need to find some special phenomenon. Yeah. So we need to consider a special situation called an indirect comparison. Indirect comparison. Yeah. Here, it's like a concept. We create that concept. Yeah. So why in our knowledge base there are so many concepts created? Why people create so many different concepts? Because we need those concepts to help us understand the problems. Here we have that situation. To understand problem better, we need a new concept called an indirect comparison concept. Okay? Direct comparison, we compare two elements directly. That's direct comparison. What do you mean indirect comparison? Here. PA greater than PB, that's direct comparison. PB greater than PC, that's direct comparison. PA greater than PC, we do not do direct comparison, but we can conclude PA greater than PC. So we call this situation indirect comparison. How about that? We do not do real comparison, right? But we have the result, PA greater than PC, as the comparison result. So how about we call indirect comparison, okay? Because our indirect way, so we do the indirect comparison through PB. How about that? Okay. PA and PC, there is no direct comparison between them directly, but there is indirect comparison passing through PB. Okay? PB is used as the stepstone to bridge that comparison, that indirect comparison. That's our understanding, is that? Yeah. So that's what we mean understanding. Okay? So we use our brain power to make some reasonable story. That's the understanding. Yeah? Yeah. We build the story. Okay? Yeah. But every step looks so natural, right? So natural. No contradiction. If there is a contradiction, then your logic thinking breaks. Okay? It does not work. So we do not allow any contradiction when we make our story. Yeah. All right, let's continue our question.
So is there like any example why to use a non-direct comparison rather than a direct comparison?
Yeah. All right. We need to make a list of convincing arguments. Okay? So in our arguments, we need to use this concept. Okay? Indirect comparison. Otherwise, people ask, you do not do those comparisons, right? Yeah. People will argue because you do not do those comparisons explicitly, right? Yeah. So we try to convince those people, okay? Although we do not do those comparisons explicitly, but we do it in a different way, indirect way. That's the way we want to convince those people, okay? Yeah. Think about it. We try to fix all the holes. This is because there is a possible hole. Yeah? People will say, yeah, I do not see you really do comparisons between those two specific players. No. Yeah. That's a potential hole. So here we use indirect comparison, this concept, to fix this hole. Okay? Yeah. Although no direct comparison, but there is indirect comparison, right? Because the result is the same. Yeah. Yeah. The path is different, right? Yeah. Path is different. Here, if I draw, direct comparison means P, you go, oh, sorry. Yeah, P, from PA to PB, you go directly, right? Yeah, that's direct comparison. But indirect comparison, you do not go directly, right? You need to go to B first, then from B to C second, okay? Indirectly. Yeah. But result, P greater than PB, that's the result. That's the same, okay? Yeah. That's the meaning. That's what we call understanding. What do you mean understanding? This is understanding. Okay? Yeah. So I want to use the example to let you see how important understanding is in our problem solving. Yeah. So we do our logical reasoning in this way. Yeah. In this way. All right? Yeah. Next. All right. Now we are ready to do the convincing argument. Now we are ready. Yeah. So after all these mental preparation, now we're ready. Yeah. The last step, convincing argument. Yeah. So I will write statement by statement. Yeah. Think about, for each statement, if it is correct, that's very important. If it is correct, each statement. All right, let's start from the first one. First statement. All right, Yeah, so that's the setup, right? We need to set up, okay? So the mean, the minimum is the final winner, okay? Yeah, so no question, right? Yeah, the minimum, the final winner, okay? Based on our, description, problem description. Second, next. The final winner, it needs to beat all the other elements in the array through comparisons, directly or indirectly. Yeah. Yeah. How do you get a final winner? That final winner needs to beat all the other players, right? But here, one special consideration we add, because for the comparison, B, what do you mean B? Comparison. Comparison result, right? Beat is the comparison result. To understand the comparison result in a precise way, we need to include one type, direct comparison. Second, indirect comparison. This is indirect comparison, right? Is that fair? Is this statement no problem? Looks all right to you? Yeah? Okay, yeah. This is our first statement, okay? All right. Now, we go to the second one. Yeah. If you feel something not quite right, you can challenge me, okay? Yeah, ask me questions. Next one. If an element loses once, it is eliminated. Is it correct? Because in your comparisons, one element may lose, then we say if that element loses just once, then it's gone to be qualified for the final winner. Is that a correct statement? Correct, right? Yeah, it loses once, you can never be the minimum, right? Yeah, because your loses once, it's greater than at least one element, right? Yeah, greater than one, so you cannot be the final winner. So this is also correct, right? No problem. Yeah. All right, next statement. Each comparison can only eliminate one element.
What are we establishing right now that those are the rules of the game before we begin the analysis?
Yes, so here, what I mean, common properties, okay? These statements, that's we so-called, yeah, because we try to establish a set of common properties satisfied by all those algorithms solving minimum problem. Yeah, common properties, yeah? Yeah. Although we do not know the details, but they all need to satisfy these statements, right? These, propositions, let's say, propositions, okay? All right, yeah. So this one a little harder to understand. Each comparison can only eliminate one element, not two. So here, or here, to be precisely, I may like to add, can only eliminate at least one, okay? Yeah. At least one means 0 or 1, okay? 0, but not 2. Yeah. This statement tells us there is no comparison. After one comparison, you eliminate both players. That's not allowed. Think about it. Can you get this one? After one comparison, so that's why we need to connect to the real world sports games. Yeah. All right. Before one particular game, two players both qualify for the final. Okay? Think about it. Let's imagine that situation. Before playing that one particular game, two players both qualify for the final. Okay? But after just one game between those players, both players are eliminated. Is that possible? No, not possible. Ridiculous, right? Before that game, both players are qualified for the final. But after one game between them, both are eliminated. Yeah. In general, it's not possible, right? But sometimes in our real situation, there is some ridiculous rule, right? Yeah, it's possible. Yeah, possible. Yeah, because sometimes when in the real world situation, people also calculate the, the small points, big points and small points. In some very complicated situation, that both players, both teams, let's say World Cup, okay, both teams could be eliminated. Yeah, so that could happen. All right, but here I talk about the generous situation. There, yeah, it cannot. Yeah, and here it cannot. Right? Yeah. So one comparison, you can only eliminate at the most one player. Okay? Winner cannot be eliminated, right? Winner eliminated, that's ridiculous, right? Yeah, based on the rule, general understanding. One game, you eliminate the winner. Something must be wrong, right? You eliminate the winner. No, you can eliminate the loser, but you cannot eliminate the winner, right? Yeah, all right. But here, I put that at the least. Yeah. So why I put that at the least? Yeah. So here you can see a lot of subtlety we need to consider. Why I put it at the least? Yeah. At the least, that means could be zero. Okay? Could be zero, that means no, how about I say this, no added loser. How about that? No added loser. You do not add a new loser. That's zero. Zero contribution to the loser. What's that? Yeah. That corresponds to a situation in our computer programming, in our computer algorithm design. Sometimes people may do the redundant work, right? Yeah. You do some comparison, but it's a redundant comparison. Unnecessary comparison. Okay? When you do unnecessary comparison, you cannot add useful information, right? Yeah. So this zero contribution of the loser means comparison. Because your algorithm design is not efficient. Your algorithm, you made some bad design. Okay? In your algorithm design, you do not remove all the redundancy, all the unnecessary comparisons. You keep some unnecessary comparisons. Then you waste some comparisons. In that situation, no contribution, no added loser after this comparison. Because if you do not do this comparison, you already know that's the result. Okay? You just redo a known result. Things like that. You redo a known result. Okay? Yeah. So that at least covering that special case. All right. Then, now the final statement. Now, we'll get to our destination soon. Final result. What's that? All right. Yeah, all right. Because each comparison can contribute at most one elimination. In our goal, how many eliminations do we need in our final step? We want to pick the final winner. That final winner should eliminate all the other players, right? How many players that final winner, the champion, needs to eliminate at the end? How many players? N-1, right? Yeah. We only keep the champion. Okay? The players other than this champion, N-1 players, must be all eliminated, right? Yeah. N-1, the number is N-1. Now the question, how many comparisons do you need to eliminate N-1? N-1. Because one comparison, you can only eliminate one, right? One comparison, you can only eliminate one. But now you need N-1, you need at least N-1 comparisons, right? Yeah. Yeah. Think about that. This is the final statement. Okay? All right. Final. We need to eliminate N-1 elements. Thus, we need at least n minus 1 comparison. The minimum n minus 1 comparisons. Yeah. Because if not the minimum, you have redundant comparisons, right? Yeah. You may have redundant comparisons. You can only do more than n minus 1. You cannot do fewer than n minus 1. Yeah. Fewer than n minus 1 because you have no chance to eliminate n minus 1 players. Okay? One comparison, the best you can get is you eliminate 1 player. Okay? If someone say, I only need to use n minus 2 comparisons, but based on our common properties, your n minus 2 comparisons, you can only eliminate n minus 2 players, right? Not n minus 1. Not enough to get a champion. Okay? Not enough to get a champion. That's the argument. So at the end, we say n minus 1 comparisons is the best solution. Nobody can do better than that. Based on these all these are common properties. Okay? Yeah. So that's the proof. So this is the rigorous proof. Okay? No hole. No hole. No. Very rigorous. Yeah. So we can get our final conclusion with confidence. All right? Yeah. So this solution is optimal. Yeah. So we will use this result in the future everywhere. Okay? Yeah. Yeah. All right. Yeah. So that's the optimality of algorithms. Okay. Not easy. Yeah. Because this question is an easy question. Yeah. Yeah. For other relatively hard questions, the optimality is very hard to prove. Very hard to prove. You need to use some very smart way. Okay? A lot of work you need to do to get a final proof. Yeah, yeah. But for this class, I do not require you to do that because that's too hard. Okay? For this class, so we only do the proof on this simple question. Yeah. So we will not do proofs for relatively hard questions. Yeah. All right. Yeah. So that's this topic. Yeah. All right. Next topic, point 2, application. We want to apply our current result, finding maximum and the minimum. Yeah. So we need to apply it. Right. All right. But so this problem actually very important for this class. Yeah. This problem very important for this class. Okay. So in our homework questions and the test questions, I will give you many questions related to this one. Okay? Yeah. But here, at this point, I want to delay this topic because I want to do the module 2, that topic. Yeah, but this one, later somewhere in module 2, so when I have a little more time, after I finish certain topics, I have some time, I will complete this one. Okay? Yeah. Yeah. So in this way, I can start module 2 a little earlier. Yeah. Now I want to go to module 2. Yeah. Yeah. This module, analysis of algorithm efficiency and the brute force method. Yeah. So this module, we will do something very special in this class. We will use some abstract notations, abstract notations to describe our algorithm efficiency. How do you represent your algorithm efficiencies? So we need to use a very abstract way. So we need to spend a lot of time to understand the abstract symbols. All right, first, part A. Yeah, we do not do that. Okay, part A. So we do our normal thing. Problem solving from experience and elimination method. Here, I want to explain the method we just use. Yeah. So in the optimality problem, I use that elimination word a lot, right? Yeah. Here, I want to talk about elimination method. This method in this class, we will use a lot. Yeah. Throughout the whole class. Yeah. Especially, remember, in the first class, I talked about in each of our big assignment and the tests, 2 big assignments and 2 tests. The final 5 questions, challenging questions. Okay? Yeah. In the first class, I said that. Those challenging questions, here, I want to let you know, those challenging questions, most of them, we need to use elimination method. Okay? Very powerful. Elimination. Yeah? If I talk about idea, very simple. You do eliminations. But you can solve a lot of challenging questions. Yeah. Elimination method. Yeah. All right, so this class, I talk about basic idea of elimination method. 8.1, selection sort. This is our first sort. Yeah. I mentioned 3 basic types of algorithm questions. Search type, selection type, sort. Yeah. We did 1 search problem, linear search, sequential search, right? We did 1 selection problem, finding the minimum. That's the selection problem. Now we do our first sort algorithm. First one. Yeah. In this class, we will learn at least 6 sorts. 6. Yeah. At least. Yeah. If I have a little more time, I will do the 7th one. Yeah. If I do not have enough time, I just do 6. This is the first one in the 6 sorts we will learn. All right. You can see the name we call it selection sort. Yeah. Sort an array, the problem. Yeah. Given an array, yeah. Unordered. Yeah. If I do not mention ordered, unordered, we mean unordered, yeah. Array. Yeah. How to sort it in ascending order. Simple problem. How to sort it. Okay? Yeah. This is our basic problem. Yeah. How to sort it in ascending order. Okay? All right. Yeah. So here, yeah, so I give you a reference. Yeah. Section 3.1. Yeah. Let's do analysis. All right. This time, now, at this point, everything we learned from Module 1 becomes our experience, right? That's our experience. Yeah. All right. Now, when we solve new computing problems, we need to use our experience. Yeah. Here, the knowledge we learned in Module 1, that's our experience. And we need to connect the dots. We need to connect to Module 1 knowledge. Yeah. All right? Yeah. All right. Now, so we need to explore the properties. Yeah. What kind of connection? So we need to do understanding. So here you can see we need to do a lot of understanding in our mind. Okay. All right. Guideline. Yeah. So that, usually these things we use as the guidelines for our general problem solving. General problem solving, we always need to do things like this. Yeah. All right. Now, and here there is another special thinking way people commonly use backward thinking. Yeah. So when we start, we from the end result. Yeah. Yeah. When we do logic reasoning, we start from the end result. How about that? Okay. So what's the end result? We imagine if the array is sorted, that's the end, right? End result. Array is sorted. And we want to see what kind of properties we can observe if the array already sorted. Yeah, that's one way to view the problem. Yeah. And here, we do some assumption. Yeah. This is a convenient assumption. This assumption, convenient assumption. We assume all the elements are distinct. Yeah. Why? Because in our discussion, if we make this assumption, then the discussion will be much easier. Because we do not need to consider the equal case. Okay? Two elements are equal. But after we solve the problem under this assumption, then if we remove this assumption, then we only need to do small adjustment. We do not need to do a lot of work. We only do small adjustment. Then we can take care of that equal case. Yeah. All right. So we make this assumption. All right. Now, to connect to our own experience, what is the related old experience? This is the related old experience. Finding the minimum. That problem is the related experience to this question. Why? Why? Yeah, let me use a diagram to show you the relationship. Yeah. All right. Now, assume, because the array has been ordered, has been sorted in ascending order like this. Okay? All right. Now, you look at this ordered array. Any interesting property you can see here? Yeah. Interesting property. Denver?
Every number in the x term is bigger than the previous term.
Yes. All right. Yeah, yes. But the direction, okay? Here, connecting the dots. Can you connect to this minimum problem? Make connection? Make connection? That's important. Yeah, because our own experience is important. You need to make the connection. Make that connection. Which is the minimum here? First. The first element in a final ordered array, the first element is the minimum. We already have the solution finding the minimum, right? We have that solution. Think of it in this way. You apply our old solution, finding the minimum first. After you find it, do you get the first element in the destination array? Yeah. This is destination array, right? Now, you apply our old solution. Yeah. So we have it, so apply it. Okay? After you apply your old solution, you get the first element in your destination array. Is there some progress? Yeah. You can place one element in your destination array. Is it nice? All right? Then the next round, you only need to find the next element in the destination array, right? Yeah? But after you put the first element in your destination array, can you do elimination? After you place first element in your destination array, it's done, right? We do not need to do anything on it, right? Can we eliminate from consideration? Okay? That's the elimination method, all right? After that elimination method, then that A1 becomes the current minimum. Can you apply our old solution, finding the minimum, to get an A1? So you use that solution another time, you can find A1. You can put an A1 in the destination position, and you can also eliminate A1, right? Can you get A2 next round? A3, another round, and so on. Can you, after you do things like this, can you put all elements in their destination locations? You solve. How about that? Okay? How about that? That's the selection sort. Because we apply the solution of selection problem. Finding the minimum, that's the selection problem. All right? Yeah? All right. Yeah. So now, based on that idea, yeah, so now I just, A0 is the minimum. Okay? So you apply the finding the minimum. The first time, you get A0. Yeah. You put it in place. All right. Yeah. Then, so here, we use a concept. Remember, this in our discussion, we need a concept called this in-place concept. Yeah? We put the element in place. Yeah. That means we put it in the final location in the final result. Yeah. That's the correct location in the final result. So we say we put it in place. Yeah. This concept. Okay? All right. Yeah. If we can put all elements in place, we get the array sorted, right? Yeah. Our goal, we put all elements in place. That means the whole array is sorted. Okay? Yeah. So we use this concept. Yeah. Yeah. All right. So usually, a special concept means we can save a lot of words. When we use this concept, we do not need to use a lot of words because this concept contains a lot of special information we need. Okay? Yeah. So we use concept. Otherwise, when we say something special, we need to explain. Okay? What's the meaning is this? Yeah. So here we give the definition. So in place definition. Okay? After we define this concept, we just leave there. Okay? Later we just use this concept in place. And we do not need to explain all the time, right? We can save a lot of words. Yeah. All right. The element is placed at the position when the array is sorted. Yeah. So that's the meaning of this in-place concept. Yeah. All right. And we also here, we use elimination method. Yeah. Every round, you need to do elimination. Yeah. Yeah. So here, these two things, yeah. Yeah. We can solve this problem. So we get a solution. All right. Yeah. The next round, we put an A1 in place. Okay. Yeah. So each round will place one element in place. Yeah. But the last round. So what is the last round? The last round. The last round, we put second to last in place because the last element we do not need a comparison. Right? Last element because only one location left. We can put it in place automatically without any work, right? Yeah. So the last element, we can put it in place immediately. Yeah. So we only need to do the last comparison. We only need to put on the compare second to last element. Yeah. All right. So then, yeah. So here, I want to do summary. Okay, so summarize the ideas that I just described it. Here, I use some diagram to describe it. All right. So this is, we treat this empty boxes as our destination array. Okay, so we want to put elements in place in these destination locations. Yeah. All right. First round, we apply finding the minimum solution. We put the first element in place. We call the min 0. Okay. After it, we eliminate this element from consideration. Then we apply another round finding the minimum solution. So we get a current minimum. Yeah, min 1. That's the current minimum. Okay. Then we put it in place. Yeah. Then we eliminate it from consideration. After it, another round, another element in place. Okay? Keep doing things like this The last one, we put it in place automatically because no need to do anything. Yeah. So the last one element, we put it in place. Yeah. Based on this diagram, now we need to count how many comparisons do we need. How many comparisons do we need? Okay? Yeah. So let's do it using our solution, finding the minimum solution. All right. When we, so here, all right. Yeah. So we have no problem on that, yeah. But now we need to do efficiency analysis. Yeah. All right, let me see. Yeah. I still have time. I try to complete this topic. All right. Now we need to count the number of comparisons. Efficiency, number of comparisons. All right. Let's count one by one. Okay. Yeah. For the first element, how many comparisons do we need? Yeah. For the second element in place, how many comparisons do we need? For each element, how many comparisons do we need? Yeah. We do that one by one. Yeah. All right. For the first one, for the first element, we need n-1 comparison, right? Yeah. Recall the total elements, there are n elements to find the minimum n-1. Okay? But the second time, for min 1, because one element is eliminated, okay? For this case, the number of elements is n-1, okay? So you use n-1 as the current element number, then you apply n-1, so this n-1 minus another one, right? Yeah. So then, to get this one, you need a n-2 here. Okay? Yeah. Then n-3, and the second to last, you need one comparison. Okay? Yeah. So then, you add up all these n-1 numbers, 1 plus 2 plus 3, consecutive positive integers, yeah, to n-1. We have a formula, right? We have a summation formula. So here we apply our summation formula. Yeah. You get 1/2 times n times n-1. Yeah. That's the total number of comparisons. Yeah. Yeah. So we complete. We find a solution. Yeah. Good or not, yeah, because there is another question. Is the solution a good one? Or another question, can we improve it? Right? Yeah. So we have a question like that. Yeah. So we need to answer that question using our whole semester. Yeah. Remember, we will learn six sorts. Yeah. Yeah. 6 sorts. The later sorts will be better than earlier sorts. Okay? All right. Yeah. So definitely, it's not the best. Later we will have many more sophisticated sorts, better than this one. Yeah. All right. But next, excuse me, I want to ask you a few more questions. Yeah. So I still have a few minutes. So I want to do some further discussion here. Yeah. Remember, we talked about some concepts before. Yeah. When we do the efficiency discussion. The best case, the worst case, and average case. Remember? When we learn that linear search, so we consider best case, worst case, and average case. Here, I also want to ask you, let's review those 3 concepts. Yeah. What is the best case? What is the worst case here? And what is the average case here? Those 3 concepts. Think about that. First, the best case. Yeah. Yeah. If the data, yeah. So you can, yeah, because the data given could be in any order, right? Yeah, arbitrary order. Is there some particular order that would result in the minimum number of comparisons? That's the best case, right? Yeah. Best case means you can choose one special input, input array. For that special input array, the number of comparisons you use for this algorithm is the minimum. That's the best case. Do we have here best case? Denver, say something?
If it's already sorted?
Not sorted. From the beginning. Okay? But you can assume at the beginning the array already sorted. Okay? You can use that as the input because ordered array could be an input, right? Yeah. Yeah. You can consider, you can use ordered array as your input. In that situation, will you get fewer number of comparisons? Ordered array, input. Think about that question. Hannes? Can I see? Yeah? Yeah. The answer, no difference. Okay? No matter what input you use, you always need to use this many comparisons based on our step-by-step details. Because every round, the first round we need n-1, no matter what is the input, you always need to use n-1. Okay? It doesn't matter. If it's already ordered, you still need to use n-1. Okay? Yeah. The second step, after your elimination, no matter what the input is, you always need to use n-2 comparisons, and so on. Okay? No difference. Yeah. No difference. So the conclusion is, for this efficiency thing, yeah, the best case, worst case, average case, all those three cases, you use the same formula, this formula. Oh, because only one case. Here, you can understand this way. There is only one case. Yeah. This formula, you get this formula. Yeah. So the best case, you get this formula. The worst case, you get this formula. The average case, also this formula. Yeah. That's the, regarding the efficiency result. That's our result, efficiency. Question?
So for the total, I'm still kind of like confused on why is there a 1/2? Like what's the general purpose of that 1/2?
1/2. Oh, this one. Let's recall. Yeah, this question, to answer this question. Remember, early, in our chessboard, that did I mention the summation formula 1 + 2 + 3? Yeah, not polynomial probably. And yeah. All right. Yeah. All right. Yeah. Let me finish it quickly. Did I mention this formula before? In our polynomial, we add up a number of multiplications. And at that time, remember, I mentioned that how to memorize this formula. We draw a diagram. Then I said, we count the number of dots. We use the, trapezoid, area of the trapezoid. Go there. Because when you apply the formula calculating the area of trapezoid, do you have that 1/2? You need 1/2, right? 1/2 times the height and sum of top base and a bottom base, right? Sum of two bases. Okay? Yeah? That's the formula of the trapezoid. In that way, you have this 1/2. Okay? Based on that, we have that 1/2. Yeah. Yeah, we can, when we derive the formula, we need this 1/2. Okay? Yeah. Yeah. All right. Yeah. Let me stop right here. Yeah. So we finish part A. So next time we start part B.